off 1.1 to look at how to evaluate limits that might be a little bit more tricky and require more methods than just direct substitution. 1.2, methods for evaluating limits. So first thing we have to consider is what's called an indeterminate form. An indeterminate form is an expression that cannot be evaluated/determined. Examples of indeterminate forms are 0 divided by 0, infinity divided by infinity, 0 to the 0th power, 0 times infinity, infinity to the 0th power. These three you won't see. These two are going to be our focus on this particular unit. So if we look at why 0 divided by 0 is an indeterminate form, first we have to note that 0 divided by any number is going to be just 0. So we should expect to get 0 here. However, any number divided by 0 is going to be undefined. So we could also get an undefined number. So depending on if we focus on the 0 on the top, we can get 0, or if we focus on the 0 in the denominator, we can get an undefined number. So we can't determine what this expression is, hence why we call it an indeterminate form. So first thing we look at is called limits by factoring rational functions. So suppose we're looking at a rational function, okay? So this method is used for rational functions. So suppose we were trying to determine the limit as x approaches 9 of x squared minus 91 over x squared minus 9x. If we plug x equals 9 to this limit, we're going to get 0 divided by 0, an indeterminate form. So we can see the function's undefined at x equals 9, but does that mean the limit is also undefined? Well, it does not. So in this particular case, what we can do is we can factor the top and the bottom to cancel out / remove common expressions to see that our limit exists. So here, what we're going to do is x squared minus a1 we can factor using a difference of squares into x plus 9 and x minus 9. The bottom, x squared minus 9x, we can factor into x times x minus 9. So right here we can see that the x minus 9s on the top and bottom can cancel out, leaving us with the limit as x approaches 9 of x plus 9 divided by x. So now we've removed our problem. Specifically, if x approaches 9 now, we're not going to get 0 divided by 0. So we end up plugging 9 in now, and we get that our limit is 2. So our function approaches a y value of 2 as x gets closer to 9. However, the function does not exist at x equals 9 because, as we noted, if we plug x right into the equation, x equals 9 right into the equation, we get an undefined number. So the limit exists using these factoring techniques, specifically 2 in this case, but the function value is undefined at that point because with function values, we just straight plug and chug to see what we get. So the next technique we look at is for limits by conjugation / rationalization. The conjugate of an expression a plus b is a minus b. We simply flip the sign of the second term. So suppose we are interested in determining the limit as x approaches 6 of 6 minus x divided by square root of x plus 30 minus 6. That's a lot to say right there. It seems quite complicated. Once again, if we plug in x equals 6 directly in this limit, we obtain the indeterminate form. So the function is undefined at this point, but as we'll see, the limit does exist. So we can circumvent this by making use of the following tricks. We multiply top and bottom by the conjugate of the expression containing the square root. In this case, the conjugate would be the conjugate of square root x plus 30 minus 6. So the conjugate would be square root of x plus 30 plus 6. We use difference of squares to simplify. Okay, we take note of that if we have a plus b times a minus b, we're going to get a squared minus b squared. And then we cancel out common terms after simplifying. Okay, so these steps might seem a bit esoteric, but they'll become more straightforward in the example that we'll showcase on the next slide. So example 2, limits by conjugation. We have the same limit here. So what we start off by doing here is we don't want to plug and chug. We're going to multiply top and bottom by the conjugate of the square root expression. So we multiply top and bottom by the square root of x plus 30 plus 6. Okay? It says minus 6 right here. That's a typo. Again, making these problems is a mental exercise right here. All right, so now what we're going to do is the top part we're going to leave alone. It's just going to be 6 minus x square root of x plus 30 plus 6. But the bottom part, what we can use now is we can use difference of squares to simplify the bottom part. Specifically, square root of x plus 30 minus 6 times square root of x plus 30 plus 6 is a difference of squares. We have a plus b times a minus b, where a is the square root of x plus 30, and then b is 6. So we're going to have the square root of x plus 30 squared minus 6 squared. which just becomes x plus 30 minus 36 because the square undoes the square root. So we're going to end up with all the same things on the numerator, but now in the bottom part, after simplifying, we end up with x plus 30 minus 36, which is equal to x minus 6. Okay? So x minus 6 will almost match up with the 6 minus x on the top part, but not exactly. We can't cancel that out. But what we can do is we can rewrite x minus 6 as minus, in parentheses, 6 minus x. If you rework that out, it's the same thing as x minus 6. So our denominator is going to become minus 6 minus x. So lastly, we get to our last step where now we cancel out the 6 minus x's, which removes the problem. Because if you notice, if we plug in x equals 6 into here, we're going to get that indeterminate form. So by doing this, we can remove our indeterminate form. So the limit as x approaches 6 of our function now is going to be equivalent to a limit of x approaches 6 negative square root of x plus 30 plus 6. We have the negative left over right here, and then we have the square root of x plus 30 plus 6 right here. So now what we can do is we can plug in 6 into this to get our limit. So we get that the negative square root of 6 plus 30, or negative square root of 36 plus 6 gives us negative 12. So this method right here might seem a little bit complicated at first, but again, the idea is to identify your conjugate, multiply top and bottom by conjugate, and then use difference of squares to simplify the resulting expression. Okay, we'll get more exposure to this in class, as it is a little bit more tricky technique to use. All right, so vertical asymptotes. Let's say instead of getting let's say when we plug in and do our techniques, instead of circumventing the 0 divided by 0, we get some number n divided by 0. What can we do in this case? So in this particular case, we can't do anything because we don't have an indeterminate form. We have n divided by 0, which we know if we divide any number that's not 0 divided by 0, we get undefined number. Okay, so in this case, what we have is what we call a vertical asymptote. A vertical asymptote of a function f is a vertical line x equals c that f approaches but never touches, where valuing the limit yields a number divided by 0. So limit as x approaches c of f of x yields n divided by 0, which gives us either plus or minus infinity. So a vertical asymptote is a vertical line at x equals c that a curve is going to approach but never going to touch. It keeps going upwards to positive infinity, which we see right here, and on the flip side, it keeps going downwards to negative infinity. Okay? So this sounds a bit esoteric, but in practice, they're not too bad to evaluate, or not too bad to determine. Okay? So we're going to use the same limit from example 1, except we're going to take the limit as x approaches 0 in this case. So again, we factor, we get x minus 9, x plus 9 on the top, and x times x minus 9 on the bottom. So we simplify by crossing out the x minus 9s on the top and bottom, but we see that as x approaches 0, there's no further simplifying that we can do here. X plus 9 and x aren't the same factor, so we can't simplify this any further. So as a result, when we plug in, we're going to get 9 divided by 0. Again, we can't do anything to get rid of this, so we see that at x equals 0, we get a vertical asymptote. This is supported by the graph of this function right here. We see that at x equals 0, we have a vertical, clicked accidentally, we have a vertical line representing a vertical asymptote. Specifically, we go to plus infinity and we go to negative infinity as we approach this vertical line. So if you can't factor or get rid of this expression right here and you end up with a number divided by 0, you have a vertical asymptote at that specific x value, x equals 0 in this case. Limits of absolute value functions. Okay, recall that the absolute value function centered at a x value c can be rewritten in terms of piecewise function, negative x minus c for x less than c and x minus c for x greater than or equal to c. As an example, x plus 6 can be rewritten as as negative x plus 6 for x less than negative 6, or x plus 6 for x greater than or equal to negative 6. Remember, the plus 6 refers to a horizontal shift of actually negative 6. So this is going to be a negative 6 right here, which we can see from the graph. Okay, so the graph supports our response here. So as a result, if we want to evaluate the limit of an absolute value function with a horizontal shift okay, let's say 6 to the left, like we see in this example. If we're interested in this limit as x approaches this boundary point, let's say -6 in this case, we must use a left-sided limit and right-sided limit to make sure a limit exists. Okay, so we'll see this in our next example here. So evaluate the limit as x approaches -3 of the absolute value of 6x plus 18 divided by x plus 3. So the first thing that we're going to do is we're going to factor out the common term of 6. Okay, so the numerator has a common term of 6. We factor that out to get 6 times x plus 3, absolute value of x plus 3, better said, divided by x plus 3. Now we can rewrite this as a piecewise function. Okay, this function ends up being equal to -6 x plus 3 divided by x plus 3 for x less than -3, and 6 times x plus 3 divided by x plus 3 for x greater than or equal to -3. Again, -3 is where we're centered at for this horizontal shift. So now what we can do is evaluate the limits by left-handed and right-handed limits, okay? So as x approaches -3 from the left, we use our left-sided function, -6x plus 3 divided by x plus 3. The x plus 3's cancel out, and we get -6, okay? Whereas if we approach from the right-hand side now, okay, we use the right-handed function, which is 6 times x plus 3 divided by x plus 3. Again, the x plus 3's cancel out, but in this case, because we have a positive sign outside, we're going to have a positive 6 as our limit. So our function approaches positive 6 as x approaches -3 from the right-hand side. So what we can see is as the left and right-handed sides limits are not equal, the limit of the absolute value function in this case does not exist. So when asked for the limit of an absolute value function, we must always break it up into piecewise functions before evaluating the limit itself. Lastly, we get to our last technique here, although this isn't really a technique. It's called the Squeeze Theorem. So let's say we have a function g of x that we're trying to evaluate the limit of. Let's say we don't know what g of x is. Okay, it's too complicated to analyze, too complicated to evaluate the limit of using any of the prior methods. So what we can do is, let's say we know that the behavior of g of x is such that g of x around our point of interest, x equals a, lies between h of x and f of x, okay? So that's our first condition, is that g of x, in order to evaluate this limit as x gets closer to a, must lie between two known functions, h of x and f of x, near the point of interest a. So what's going to happen now is that if h of x has the same limit as f of x, okay, aka as x approaches a for h of x and x approaches a for h of x, they both approach f of x, they both approach the same value L. What that means is that since g of x is between h of x and f of x, that forces g of x to have the same limit as h of x and f of x. Hence why we call it the Squeeze Theorem, or also known as the Sandwich Theorem. Because g of x gets sandwiched between. So because h of x and f of x both have the same limit, and g of x is located between the two functions near that point of interest for our limit, that dictates that the limit as x approaches a of our function g of x must also be equal to the limits of h of x and f of x, specifically L. Note that both of these conditions must be specifically met. So if g of x is between h of x and f of x, but let's say f of x and h of x do not have the same limit, then that's going to provide some wiggle room for g of x to be anything between the two limits of h of x and f of x. So as a result, the limit of g of x could be anything between the limit of h of x and f of x, but we don't have a definite answer for what g of x is. So by requiring the second condition, that squeezes g of x to be a specific limit as opposed to just being a range of possible values. So both step 1 and step 2 must be used in order to meet the Squeeze Theorem. And these are our methods for evaluating limits.